Folks, let's get started. So welcome to the undergraduate research experience presentations, where folks to describe the work that you did under the CNRE program this semester. So thank you all for being part of it, first of all, and for the work that you did. And I hope you found it enjoyable and interesting, worthwhile experience. Yeah. So we emailed out an agenda. That's the speaking order. And I'll just go through it quickly. So Amy, followed by Vaibhav, Chelsea, Megan, and then Jack. Jack will be here, so Gary and Xianzhang will describe what he did. Your talks are all 10 minutes, including questions. You would have received, we'd like your feedback on the process, so please do respond to Kavita. Yeah. And if there's anything you'd like to share, apart from the specific questions asked, please let us know. And if this is something you'd like to pursue next semester, also let us know. Okay? If your schedule allows it and it's something you'd like to do, let us know. Contact me or Kavita. We also emailed, sent out an email with applications for the summer. You were interested. Okay, in terms of presenting, we're sharing it via Zoom, so that there are some people who are online remotely. So please just, before you come up, just share your talk on Zoom and just come up here and you should work fine. And please mute your speaker, so you're using the speaker in the room, so there's no feedback. That's it. So our first speaker is Amy Fahmy, talking about identical inspired design on pitching foils and choirs.
Hi everyone, I'm Amy. So like you said, the project that I've been working on over the past semester is determining the impact of dental-inspired designs on a pitching foil and fluorescent foil. So this research was done under the guidance of Lukesh Sowell and Xianzhang. So let's just start off with some background. So denticles are these tube-like structures found in nature on shark skin, and they've been largely credited for these efficiency of sharks, and they're also important for their drag properties. So we believe that these denticles have potential applications for thrust production. So this project is specifically relevant for marine propulsion and renewable energy industries, and it's to lead to the goal of creating more energy efficient propulsion applications. So within the structure so in 2018, Gomel tested these denticles on rigid foils, static rigid foils. So he placed them on the suction side and he tested 20 different foil designs with, and he found that in general denticles do improve the aerodynamic performance on static foils, but specifically the most efficient design was one row of ridges 55% away from the leading edge of the foil. 55% of the core away from the leading edge of the foil. And what he expected to see was the drag reduction, which he did see. And this is because of the streamlined vortices that occur because of the ridges on the denticles themselves. And these replenish the boundary layer of the foil and therefore reduce the drag on the foil. But what he didn't expect to see was the coefficient of lift that increased in this study. So specifically at lower angles of attack, it's not common to see like that, and what they hypothesized was this was due to the separation bubble that formed behind the denticle, and he theorized that this separation bubble created suction, and therefore generated lift on the foil. So we see this aerodynamic increase. Specifically, they use the coefficient of lift divided by the coefficient of drag, and they see this increase from 0 to 15 degrees of angle change. So Offner in 2012 also investigated the swimming performance of flexible foils without denticles, with and without denticles, and they found that the swimming performance improved with the denticles present, but they didn't share any of their parameters, so you have to take this study with kind of a grain of salt. So now the question is, how do these densical inspired ridges affect the hydrodynamic efficiency of an oscillating coil in a zero flow condition or a ideal flow state? So we conducted our experiments on a rigid pitching coil, and we did this because they are shown to imitate the movements of caudal fins on fish, and they're also shown to be more efficient than traditional propulsion methods. So we apply the continuous densical inspired profile, 55% of the cord away from the leading edge of the foil, and we matched all of our non-dimensional parameters with Gomel's most efficient trial. So the ridges themselves protrude 0.7 millimeters above the surface of the foil itself. And we tested from a range of Reynolds numbers, specifically based on the velocity on the trailing edge, from 3,700 to 20,000. We kept our maximum amplitude constant at 15 degrees, and we can change our frequency in order to change the Reynolds number. We can use the setup shown on the left in order to simultaneously take force measurements and flow field measurements. So you take flow field measurements using particle image velocimetry, and that's essentially the process of distributing tiny plastic particles through water and illuminating them with a laser plane. And then at the same time, you can take camera images and you can track the movement of these particles through as the foil oscillates, and you can use this to create a flow field. So let's look at a case for a Reynolds number of 3,700. On the left, you'll see the phase average flow field data over 80 to 90 cycles of oscillation. And then to quantify this data, we can divide up the flow field based on distances away from the foil. So on the left, we can see that the ridge foil seems to maintain the velocity farther out than the smooth foil. And we can also see this reflected in the bottom right figure. So this implies that there will be an increase in thrust production for the ridge foil as compared to the smooth foil. And let's look at a case for a Reynolds number of 10,000. So here we don't see the same effect. We see the smooth foil kind of meander down a little bit, but regardless, if we look at the bottom right figure again, we can see that although they're kind of declining at the same rate, the velocities for the ridge foil start off lower initially and decline kind of steeper in the first half. So we see that the smooth foil is maintaining velocity farther out. So to confirm this, we can look at our preliminary force measurements. So the figure shows the phase average data over 80 to 90 cycles of data again, condensed into a single cycle of oscillation. So we see some variation in the force on the foil as it oscillates, which is as expected. And then we can take the average of this and use it to calculate the coefficient of thrust at each Reynolds number. So we see that as expected at a Reynolds number of 3,700, the ridge foil is significantly increased as compared to the smooth foil. And then at a Reynolds number of 10,000 to 20,000, our work is inconclusive. So we don't see significant increase and a significant increase or decrease in the coefficient of thrust of the smooth foil as compared to the ridge foil. So in conclusion, densical inspired designs do show promise for improving the hydrofoil efficiency, specifically in this case, enhancing the thrust of a hydrofoil. And our findings so far suggest that ridges could improve thrust and at lower Reynolds numbers. So we plan to further explore different ridge sizes, shapes, and locations on the foil itself to optimize the placement for propulsion. And then I would be happy to answer any questions.
Other questions for you?
How did you manufacture the denticles? Were they 3D printed?
They were 3D printed. So we used, I believe, I don't remember the exact material, but it was a resin-based 3D prints. I think SLA.
And then did you print them directly on the foil itself, or did you like attach them all?
We printed
After
them on
the
a
fact.
foil. So we printed, if the foil is, the flat side of the foil is printed, and then we sanded down the bottom. If that makes sense.
You showed the benefit of the ridge foil at low Reynolds number. What are the potential applications for real life propulsion system that has a similar Reynolds number? And also, are there any similarity for flat wing flight where they see lift performance increase by having a continuous growth of leading edge vortex, where in this case it's like mid chord vortex structure formed by the separation?
So these experiments were performed in an ideal flow state, so we don't exactly know how they would relate to real world applications yet. But they would specifically be relevant to, pitching marine designs, and also, I would say, wave energy designs as well that move down. And then, what was your second question? I'm sorry.
Is there any similarity to a bird flat wing flight where there's like a leading edge vortex right from the start of the leading edge versus this where there's a mid chord sort of vortical structure forming?
I'm actually not sure. I'm sorry.
What 55% of the code? Like,
It was just the most efficient case in Bill Mell's trial. So on the static foil, with flow coming past it, they found that 55% of the core with one row of bridges was the most efficient trial. So.
Good.
Okay, hi everyone. I'm going to be talking about using compressible LES and towards the end a little bit about machine learning to model cavitation on an ECHA 0015 hydrofoil. I worked with Professor Mahesh Sagnam, who's in Korea, and Gary and Xianzhang throughout this semester. The brief overview of the problem. I was investigating the cavitation mechanism, which occurs when the pressure of a liquid drops below vapor pressure and causes the formation of vapor bubbles, which we usually refer to as cavities. And these have very complex flow mechanisms. To quantify cavitation, we usually use the cavitation number, which is dependent on the free stream pressure, vapor pressure, and free stream velocity. And usually a higher cavitation number means less cavitation, and a lower cavitation number means more cavitation. The collapse of vapor bubbles or cavities can create high pressure waves, which result in noise erosion, which we can see in this propeller right here. The brief overview of what's been done so far. The LES model that I'm using, the predictor corrector method to solve Navier-Stokes equation and transfer equation for vapor mass fraction. If you take a look down here, you can see that the model has been validated with experimental data. Development in started kind of with modeling cavitation over a wedge. And you can see this cavity growing and then eventually reaching a critical length and then breaking off into a cloud. And then it's the collapse of this cavity that is responsible for erosion. And the pinch off from sheet to cloud can be determined by either bubbly shock or a re-entering step. And usually at lower cavitation numbers, we see the propagating shock waves. The goals of this study was to look at an ECHA 001 hydrofoil in an unconfined domain with span-wise periodicity. It's a 2D simulation with 3 different cavitation numbers and 3 different angle of attacks. And ultimately, it seeks to answer the question, how does changing cavitation affect the lift coefficient? So if you take a look at this table, these are the 3 cavitation numbers that I was experimenting with, and these are the angle of attacks. So the first step was to create a mesh, and my method for doing this was to create boundaries that are far enough from hydrofoil so that once the cavities collapse, the pressure waves that are caused by them don't actually reflect and affect the hydrofoil. So the boundary conditions I used were a sponge layer in the inflow and outflow, and no slip walls at the top and bottom of the domain. And then, of course, periodicity in y direction. This figure here is just the transient pressure wave to just demonstrate all of the boundary conditions. Usually the pressure waves in the experiment aren't actually that large. So here's just a brief overview of the mesh for the 0-degree angle of attack and all the boundary conditions that I used. And then, of course, this is for a 3-degree angle of attack and a 7-degree angle of attack. And then, of course, the final step was to extrude it by 1 unit and assign significant units in y direction, and then partition the mesh so that I can actually submit it. So this is kind of the result of the simulation. You can see for 0-degree angle of attack, there isn't any cavitation. We sort of start to see it at lower sigma for higher angle of attack, and then especially for a 7-degree angle of attack, we get very obvious sheet to cloud transitioning for both 0.6 and 0.9. The point of having this at such a high cavitation number is kind of just to have a case without any cavitation. So for data analysis, I used TechPlot and MATLAB. TechPlot was used to make the contour plots, and MATLAB was to generate graphs of the lift coefficient versus normalized time units, and also the mean lift coefficient for each angle of attack and cavitation number, and then plot that against the angle of attack. So for a 0-degree angle of attack, there was no cavitation for any of the cases, and the lift coefficient was consistent throughout all of the cases, but the time histories for each case was different, which implies that lack of visible cavitation doesn't mean that all of these cases are identical, as expected, because the different stream pressures affect the velocity, pressure, and vapor volume fraction. This is the lowest. You can kind of see in the transient step, there's a little bit of cavitation in the trailing edge, but that disappears pretty quickly. For a 3-degree angle of attack, a little bit of cavitation is seen for sigma is equal to 0.9 and 0.6, but for 0.6, there was sheet to cloud transitioning, which indicates that there would be more propagating pressure waves. And there were also greater oscillations in the lift coefficient versus normalized. Also, to point out, there's also a significant decrease in the average lift coefficient. And this kind of shows the sheet to cloud transition. It's a little small, but you take a look at it. For the 7-degree angle of attack, cavitation was seen for both 0.9 and 0.6, and there was sheet to cloud transitioning for both of them. There's a more visible decrease in frequency now. And as expected, the cavity is largest for sigma equal to 0.6. And again, just like the 3-degree case, we have a significant decrease in the average lift coefficient at lower cavitation numbers. And here you can see 2 cases of sheet to cloud transitioning. Let that play. So a summary kind of was for the non-cavitating case, and then the sigma is equal to 0.9. We kind of see linear behavior in the lift coefficient versus the angle of attack. If you take a look here, and obviously we see a decrease in the slope, but we also see a deviation from linear behavior as we get to lower cavitation numbers. So the conclusion of this is for cavitating cases, we see a decrease in the frequency of the lift coefficient and increases in amplitude where cavitation is present. In addition, the linear behavior exists for non-cavitating cases, and at lower cavitation numbers, we see the deviation. So the next steps are now to incorporate machine learning using these LES results. And we're kind of thinking of dividing it into two different problems. The main focus is to predict wall pressure fluctuations. One method would be using contour plots of void fractions, like those images that I showed earlier. And the other method is to use void fraction data. For using contour plots, previous work done in bubble pattern recognition using convolutional neural networks can help inform what techniques we might want to use. And in regards to using void fraction data, the approach is to extract the data from the overset mesh in the zones nearest to the hydrofoil wall, and mainly looking at the nearest cell pressure value and cavitation away from the hydrofoil wall. We also want to utilize any existing empirical models that discuss the relationship between void fraction and wall pressure fluctuations. And then finally, to set up the model, we kind of want to establish a basic sense of relationships and determine what input parameters we want to use. So right now we're thinking of examining relationships between cavity size and time and distance to the hydrofoil and pressure at the hydrofoil. So yeah, thank you to all the faculty and postdocs who helped me out.
It was interesting to see like there's a huge spikes, like 2 spikes in the
Yeah.
cavitating. So what is the frequency of that, and how do that correspond to your observed animation? Is it like
Here?
Yes.
I haven't done FFT on this yet, so I'm not sure.
It seems to be a very large time scale. Right? Like,
Yeah, it is really large. Yeah, I think without running FFT on it first, it would be kind of hard to say. But
But would you have enough data to do FFT if your time zero only have 2 occurrences?
I'm not sure. That's more of a Sangam question.
I mean, you can visually extract it.
Yeah.
If you believe this
Yeah.
is going to be repeated, it's about 15.
Yeah.
C over U infinities.
Is this like a bursting of the entire sheet or like a pinch off?
Something to look at.
Yeah. And this shedding is not the whole cycle. This animation, at least. So yeah.
Why would the onset of cavitation increase later?
Increase?
Yeah, that's what you mentioned. Maybe I missed it.
I said decrease
Oh,
as cavitation. Yeah. So at lower cavitation numbers, there's a higher presence of cavitation on the hydrofoil, and then that decreases.
The mean lift goes down, what he's showing, the fluctuations go up.
I see.
Okay, very good. Thanks, Vaibhav. So the next speaker is Chelsea, talking about producing synthetic algae for biofarming performance. Yeah, you go to slideshow.
So this past semester, I've been working with Don Harish and Pribak to produce synthetic algae for biofouling performance tests. So some background information, biofouling is the accumulation of organisms on ship hulls, and this really affects the performance of ships. It really decreases the drag, or it increases the drag on the ship and decreases the performance. And testing with real algae is really difficult just because algae is really hard to work with. And we want to model how the effects that algae has on drag in a repeatable and systematic way. And because algae is difficult to work with, we wanted to create a synthetic algae for testing. So in order to create a synthetic algae, we decided to use hydrogels to see if we can create a hydrogel that has the same material characteristic as algae. And then eventually, after we create these hydrogels, we'll test the drag they cause using flow measurements with the particle image velocimetry techniques in the MHL. So this image is just a steel plate that has some of our hydrogel samples on it. And this is like a very early on mock-up of what will be used to test the drag. So some literature we've referenced are these two papers that basically describe the different methods on how to develop hydrogels. So the main hydrogels we are using are calcium alginate and carrageenan, and they just explain how to make the different hydrogels. So we spent most of the semester trying to figure out how to actually produce the hydrogels. Even with the papers, some information was just missing, so then sometimes our hydrogels didn't come out as expected. So our very first sample, our hydrogel actually evaporated while we were letting it stir at 90 degrees. And then a couple more evaporated after that. But yeah. So we were originally using just alginate and carrageenan to make alginate hydrogels and carrageenan hydrogels. The carrageenan hydrogels were working, but the alginate ones weren't. So we eventually had to buy calcium chloride to mix in with alginate to make calcium alginate hydrogels in order for it to gelify. So there are different approaches we use to making the hydrogels. So we tested a ton of different concentrations, and we also use for the alginate, we use different methods of mixing or like pouring things together. And then at the end, when we had the samples, we submerged them in water for a different amount of times in order to replicate the conditions of the water channel testing for when we eventually do test them for drag. So that image shows how the hydrogel changes between being submerged in water and not being submerged. So in order to characterize these samples, we use the dynamic mechanical analysis machine in the NGG round, which basically just gives us a stress and strain of the different samples. So this is our sample in the machine. It basically just gets pressed and then unpressed, and we model the results there. And from this graph, we can get the Young's modulus of the samples. So we haven't really done much other than that because it has been really difficult to make the model. We've had a lot of limited times and a lot of limited molds. So to make the carrageenan sample, that takes 2 days. And for most of the semester, up until like this week, we only had 4 molds, as that image shows. But this week, we tested with this new mold. And I think we'll start making new molds so we can start producing more samples at a larger scale. And then the samples can only be tested once because the characteristics, because it's getting pressed and then uncompressed, some things might like change in the material. So it's like a one and done. And then the hydrogels are very time sensitive. They'll begin drying out. And it's also pretty difficult to create uniform shapes with them. So at the end of the semester, we finally figured out a way to properly make the different hydrogels. And once more samples are made and characterized, we will start using them in the water channel, which is the MHL. And yeah, we'll test the hydrogels on the plate in different arrangements. So either uniformly or non-uniformly because algae grows non-uniformly. And then we'll also use synthetic streamers to better replicate the characteristics of algae. Thank you for everyone. This semester.
I'm wondering what the connection between the like mechanical properties, like stress strain, is to the hydrodynamic properties that you're going to be testing in the SF3 later.
We're doing the stress strain test in order to match the hydrogels to algae. I don't think it's related to the hydrodynamic test.
What was the question?
Like I'm wondering what the relationship between the like mechanical properties of the hydrogel is and the hydrodynamic properties in like how it responds to shear stress on the wall.
Yeah, I think basically what Chelsea said. So we don't want something that is too hard, for example, and those samples need to be compliant and need to sort of behave like the real thing. So that's why first we need to see how much material do we need to add, for example. So what Chelsea said.
So did you have a control of like algae, and then you tried to like match the samples to that control?
I know Rodrigo's been working with algae in the Key West, but here we don't have algae.
Yeah, so basically the work that we are doing in Key West is with real fouling. And the idea that we have is to scan the configuration of the fouling on the plates and then replicate that with the synthetic samples that we are making.
So to add to this, estimating the mechanical property of this fouling is really difficult. So what they have done, which is I think pretty amazing in the past 4 months, is to actually make something that sort of resembles an algae in the lab, so that we can take it and code it the way we want and do hydrodynamic testing and see how those properties result in hydrodynamic performance. And then go do cyclic.
How?
So do you have data available that you're comparing to for the mechanical properties of the algae itself?
Not yet.
So that's something that's also.
Like, how do you intend to like make compliant streamers out of the hydrogel? How would that work?
I mean, yeah. So nobody used the word streamer except Swami because you worked on this problem before. No, that will be later.
Okay.
But the plan is to have a streamy surface and then put these hydrogels on them so that you have both compliance and streaming.
Okay.
Yeah, there are several techniques that we have seen in some papers where they can make them in a nice and replicable way. I can even send you the paper if you want. It's quite a chemical process to make them.
I think right now, like she said, scale it up, test the properties, see what we learn, go from there. Very good. Thank you. Oh,
One last quick. Do those gels stick to the testing surface?
No, they don't. Gluing them down.
Yeah. You go to the first image. That's basically with water-based glue, which is a common way of sticking them into the surface.
Yeah, they will do that next semester.
Yeah.
Test it.
Because in some cases we are actually going to want the samples to get out with the water, because that's actually what happens when you have real algae, and that's what makes it very difficult to actually test with real algae.
okay. Thanks. Megan? The next talk is what? Speak on harvesting, transverse flux temperatures. Could share your talk with me.
Hi, my name is Megan, and today I'm going to be talking about the research I did on underwater current energy harvesting with a transverse flux generator. So, some background. Arctic Ocean currents, they are a reliable power source for sensing systems monitoring, and they also change beneath Arctic ice. So the question here is, how can we effectively harvest this energy? And one of the solutions that we came up with is using a flux generator. A flux generator can generate a useful amount of power even under very low RPM, which these Arctic Ocean currents are very slow. The target speed is around 0.2 meters per second, but the flux generator it usually operates around 0.5 meters per second. It also has a high magnetic flux density, which is really good for slow energy applications. This means that the magnetic field is more concentrated, so there's more efficient power generation. The figure on the right, you can kind of see just an example of how a ocean current generator would operate. So there was a previous design of this flux generator, but there was quite a few issues with it. You can see in the photo that there's an outside casing, and then there's stators in the middle with a copper winding wrapped around them. The copper winding had to be wrapped inside of the case, which just made it very hard to assemble the stators within the case, also rocked back and forth. And cogging torque was too large, which I will touch on what cogging torque is in a little bit. So kind of the working principle of the generator. It's basically just Faraday's law of electromagnetic induction. The stators, which are iron cores, they pass over magnets that have alternating poles, and this will induce a magnetic field and thus produces alternating current within the copper windings. And this generates energy. So the goals that I had for this project was design a generator that contains a C-shaped stator core, rotor permanent magnet, stator coil, and motor shaft access. But the main challenge here that I wanted to solve that would kind of differentiate this project between previous students' work is that I really wanted to decrease cogging torque. So what cogging torque is, it's the interaction between the permanent magnets and the rotor and the iron core stators. So the iron cores, they're attracted to the magnets. So when it passes over a magnet, that magnet's going to want to pull back the iron core. If the attraction is too strong, then this is going to cause what is called cogging torque, which is, you can feel it when you're turning it, that the magnet just wants to pull back the iron core to the magnet. And so the main objective here is how can we optimally harness this energy? Just from some prior research, we'll get into it, but you can skew the stators relative to each other or find an optimal air gap to decrease that magnetic attraction. So some literature review that I had done, this paper talks about offsetting the magnets' positions relative to each other. If you think about it, there's stators on either side of the casing. If one's passing over a magnet on one side and it's trying to attract back, but then the other one has the opposite attraction towards it, it's going to cancel each other out, which I'll get into a little bit more detail later. And then another paper I read was on changing the magnets itself, but I decided not to move forward with this because the cogging torque reduction was just not enough in this case. And then the figure 8, you can kind of see how industry generators tend to skew their generators, but what I did was a little bit different. Show you. So how did I go about designing this generator? It was designed in SolidWorks. There was multiple different prototypes, designs done, 3D printed, multiple test pieces. And kind of the procedure that I went about for this is that I wanted to identify areas where the generator needed to be improved, which I stated kind of back in the first slide. The winding, the copper wire, ease of assembly, cogging torque, all of that. So kind of the first design iteration, I moved the ball bearing to the outside to kind of take account all those things. Also using a key shaft, I created a winding ring, so you don't have to wind the copper wire inside the case. You can do it outside, and then you can just fit it into the case. You can see in figure 12. I also focused on reducing cogging. Kind of the working principle of cogging you can see in figure 11. The green sine wave line would be the magnetic attraction force if there's no skew. Also, the top of the figure, that's the skew implementation. The red and blue squares are the magnets, and then the black U-shaped looking things are the stators. That's the skew, because they're offset from each other. The red sine wave line would the magnetic attraction force of the top stator, or I guess the one that's passing over the red magnet, and then the bottom one, the blue one, would be the one that's passing over the blue magnet. So those sine waves effectively cancel each other out, and you can get theoretically zero Cogging torque, but that's not really the case in actual application, which you can see in Figure 6. Cogging torque, finite element analysis, and then experimental results. It's not effectively zero. So results from my design. I, again, skewed the stators to be out of phase. You can kind of see the stator peeking out from the generator case. They're not directly on top of each other. This can cancel out the attraction force and less cogging. I also wanted to tackle the air gap issue. You don't just want to make the air gap as big as possible, because then you're going to have a smaller magnetic field and thus less energy harvesting. And the air gap can depend on many different factors. The torque, how fast the generator is running. So it can change depending on the application. So I wanted to create a variable air gap design where you could change it depending on the application that you're using the generator in. So basically, you can unscrew part of the outside of the generator case, and this will push apart the case from each other. And you can make the air gap bigger or smaller depending on the application that you want. And this helps tremendously with cogging torque, because the skew cannot, even theoretically, it can cancel out cogging torque 100%. It doesn't in actuality. So some limitations of the design. Cogging is still present. You can't really 100% eliminate it. There's also different kinds of flux generators. Mine I'm using is a axial. There's also a radial. This can be better in certain applications. Another big limitation of the axial generator is that the turbine cannot be easily integrated within the generator. You need the turbine to capture the Arctic current. The generator can just turn it on its own. With the radial flux generator, since there's no middle plate where the magnets are, you can just easily integrate the turbine into the middle. And this kind of is also another reason why the axial generator is challenging to manufacture. You also have to have a lot of precise alignments, which is definitely one of my biggest challenges with this project. An impact of this is that optimal energy harvesting can maybe not be met. Things on the left, I think I've already kind of touched on. So conclusions from this project. The cogging torque can be significantly reduced due to skewing of the stators and a variable air gap design. The implications of this is that transverse axial flux generators are a viable option for slow speed systems and for energy harvesting. Some applications for this, I don't have the final prototype here right now because somebody else is using it, but it is printed. There's some small things we have to change for it, and we also need to do testing on it. We'll get to that later. But after we finish testing, this is going to be sent to Alaska. It's going to be tested in the Arctic Ocean. This is good because there's constant ocean currents in the water, and the water speed's very slow, around 0.2 meters per second, which is perfect for the application for this generator. Some future work. The turbine design, although that's kind of out of scope for my project, is very important. That's how you capture the underwater current. Some other people in my group, they're working on a radial generator design. We're going to kind of test these two in tandem in the Arctic, I believe. And then maybe we can go over further cogging torque reduction methods. Like previously I talked about changing the magnets. We also need to do more thorough data analysis on this turbine. We have already set up some ideas of some tests we're going to do. We'll do an experimental dry test setup, no turbine, just drive the generator using motor under torque control, and vary the load resistance to find max output power under torque, input torque. We're also going to collect the data acquisition system and parse the data in MATLAB, and then find the optimal air gap under different rotational speeds and different input torques. And thank you for everybody who's helped me on this project.
Time for two quick questions.
I guess, what are the major ways in which this generator is different from other generators on the market? Like, why were you not able to just take something off the shelf?
I think the biggest thing is the slow speed of the current that we're trying to harvest energy from. Most generators are not going to produce any sort of useful energy production under that slow of a rotational speed.
How big of a turbine do you need, or like is that like also like are you also working the turbine to capture?
So the previous master student who kind of worked on some of this, he had a turbine, which this is kind of like a good size comparison from the generator to the turbine. There's also going to be like a funnel that will like funnel the water in, and that will increase the speed of the water too. But that's besides the point. I have not really worked on the turbine, also a little bit out of scope for me, but I think this is kind of a good size comparison, turbine that and the generator.
Okay, thanks, Mike. Okay, the next talk is by Jack, who couldn't be here today. And so Gary and Xianzhang will speak on his behalf. And the title of his work is titled Sensitivity Analysis of Physics Informed Neural Networks. You don't need to plug the labyrinth. Don't plug that in.
Okay.
Just share it also.
Sure.
Oh.
Yeah, so hello everyone, I'm Xianzhang.
My name is Gary.
So we are both postdocs. We work with Professor Mahesh, and so today we will present Jack's work for this semester at CNRE, sensitivity analysis of fixed informed neural networks. This is how Jack looks like. So because Jack cannot make it today, so we will present his work on his behalf. And Jack is a junior undergraduate student from industrial and operation engineering. So before Jack came to the CNRE, I have to mention that Jack knows nothing about either neural networks or fluid mechanics. But after as of learning and research by Jack, now he understands basically what are physically informed neural networks means. So compared to other deep learning neural networks, the physically informed neural networks use the loss function to penalize the errors based on both data and the physical loss, which is the PDE that is programmed into the neural networks as an additional loss function to perform to see how well the network is performing. And so as you can see here, the loss function of pain contains two main parts. One is the data loss from the data we collected, and the other one is the physical loss, which includes the governing equation, initial condition, and boundary condition. So for Jack, the question is he wants to know how does the sampling of the spatial and temporal data affect the trained Payne's model. So to be more specific, as we can see here, the example of the sample points are correlation. So the pins, the sampling points we mentioned here, it contains the collection point for PDE, so which means you can randomly select the spatial and temporal points to calculate the PDEs. And then meanwhile, you have some sampling points from the data collection, which is here you have the initial condition points and some boundary condition points you collected. So Jack wants to know basically how does the number of sampling points affect the loss function value? And if we given the same number of sample points, will the output differ and to what magnitude? And given the same like number of sample points and seed, which is a pseudo random generator in the training model, and will the output differ and to what magnitude? But the most interest problem is I want to know how does the uniform sampling and random sampling affect the training model. And then, so basically, these are two relevant literature. The first one is the original paper in 2019 and introduced basically the structure of the pin and also and the other one is a paper found by Jack. There are some people have looked at the different sampling method to gather the data points and they compare both uniform sampling and non-uniform sampling method. So this is what actually the next plan for Jack to study on that. But we have done some premium work. So so Jack decided to start working with the 1D forward continuous Burgers equation, which is useful for building the blocks for fluid dynamics. And so when here is basically the Burgers equation with the PDEs and initial condition and boundary condition. And there are two quantities we want to check for the performance of the pin, which is the alternative arrow of the solution U, and the other one is the how the PDE function works. And this work is code is modified based on an open source project on the GitHub, and then Jack adds some additional features on the code and also on the plotting asset. So basically, we observe the loss function values in terminal plot of and the plotting of the output, as you can see here, and created by the pins training after running with NVIDIA A2000 GPU. So basically, as you can see here, this is a validation result that the pins can successfully match very well with the exact solution, and the error of the solution goes down to 0.04, and the validation loss is as low as 8.07 to the -4. So then the next part, Gary will talk more about the result and discussion.
Thank you, Xianzhang, for the introduction and methodology. Next, I will just walk us through some detailed result interpretation. In addressing to our research question on how something affects this performance of this relative new tool, the first set of study is to systematically increase the number of random points selected in space and time. And we compare this, so Jack did a series of study by increasing the random sample points from 1 to 50,000. And the training results from the model are plotted in this figure here. They're showing three different quantities. The first line is tracking the L2 norm of the relative errors, comparing the model and exact solution. As you can see, it decays with increasing number of sample points in a relative -1/3 slope. And then the second line showing in orange is showing the mean square of the absolute errors for these cases. They decay to -2/3 to -1. And then also interestingly, this is the final training result, but it's not the optimal result. So prior to the end of this training session, the system also reported the optimal loss value, which is also lower than the orange curve. So this is indicating some overfitting in terms of the model output. More interestingly, we also observe a strange kink point at this case where the sample size is around 1,000 points. And we think we then delve into detail in understanding what produces this kink point. So it turns out by varying the number of random points selected in space and time, we have used a pseudo-random generator, and this random generator is controlled by a seed. This seed not only controls the random selection of points, it also selects a random initialization of the neural net parameters. So basically, the kink point is a product of these two variability. So confirm this, Jack then did two sets of tests. So first, you control the same random points and the same random initialization of the neural net. And he observed results are identical. So this suggests pin optimization is not stochastic. The second test is to use the same random points, but then different neural net initialization. And he observed a various range of training results are shown by the right figure. So he did five different realizations of the random initialization of the neural net, and then comparing the three major quantities in those color bars. As you can see, with different random initialization, you can observe as much as 1 order of magnitude difference in the training results for this relatively simple test case. The second point of study is to kind of investigate how does the nature of the sampling in space and time affect the training results. So specifically, we're comparing using the same number of points, but either randomly select them or uniformly select them. Surprisingly, for the same random initialization of the network, uniform sampling actually performs worse than random sampling. We then asked Jack to kind of check another different initialization, and that's kind of the optimal uniform sampling result. As you can see by comparing blue and dashed curves, the training result is not as good as random sampling at all. So we're wondering whether this problem specific related to the mathematics or the architecture of the neural net, whether random initialization statistically hold true for this kind of behavior. This leads to our conclusion and future work. So we decided to choose 1D Burger's equation and use it as a gauging tool to evaluate the performance and characteristics of PIN for data assimilation. So Jack focused on two aspects. One is the random initialization of the neural net parameters, and he showed there are significant variability in the training results. Two is comparing whether using uniform or random sampling, and that also plays an important role. And surprisingly, random sampling performs better than uniform sampling. This seems to be supported by studies by Rassi and Wu et al. So in the second work, the authors suggested using adaptive sampling. So the idea is you pause training in the middle, look at the loss function, and observe their spatial structures. And then you refine the sampling points around the worst performing region. So that's kind of the next step. And another future work direction is to see whether PIN can be used to train predictable knowledge. For example, for this test case, 1D Burger's equation would admit a series of similarity solutions. So I'm wondering whether training on one solution, can the model be used to predict the same set of family of similarity solution for next step?
Thank you, guys.
Thank you everyone for listening. Acknowledgement and
Okay, questions? Time for two quick questions.
How do you quantify the data loss function? That first slide.
Oh, the data loss function is basically you calculate the mean square error of you're collecting the you predict data from the model and then some sampling data you collect from the real data.
Does it vary if you have CF data versus experimental data?
Right now, these are just take like equally weight, so they're equally considered. And yeah, so another thing like we are trying to do is also trying to adjust the weight of the loss and see how it works. Yeah, but right now it's equally weighted. Yeah.
You were showing the results. You showed something called, when you're talking about overfitting, you mentioned an optimal loss. What do you mean by that?
Oh, I answered that question. When you train the model, so the training and validation is like the validation here in the machine learning is kind of a part of the training. So when you just keep training your model, but then every time you check your validation result. So like you just give the maximum iteration you want to train, and you'll find like it's not the more you train and then the better result you got. So in the middle of some point, some iteration, that's actually the best validation result you obtain from your training model. Yep.
Okay.
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 Okay, that's quick.
No, it's fine. It's fine.
You seem crestfallen.
I was just wondering if when you talk about increasing the number of sample points, is that the sample points used for evaluating the data error, or is the same points used to evaluate the data error also the points used to discretize the solution to evaluate the PDE? Does that make sense?
Yes. So the sampling point, he basically increased here. So you can Like this is the red dot here, the sampling point inside the frame. But every time you keep the same initial and boundary number of points, and when he increased that, like here, he increased the sample point on this red dot here is the sample point for the training. So when you train, like you try to collect more information from your training data. That's the sample points numbers.
Okay.
So
those sample points, they're evaluated against the PDE, and then those terms kind of provide information on how you update the parameters in the network.
Yeah.
So yeah.
Okay, thank you all. Thank you. I really want to thank